Hello and welcome everyone. So from this session onwards, we'll be dwelling into the parallel track of machine learning. So this will be the introductory lecture on machine learning. And as previously said that this lecture, what are we going to study in this lecture? What are we going to learn? So most of these terminologies will be used in most of these lectures. So whatever we are going to study after this, so whatever terminology I'll explain today, so most of them will be used throughout the course. Okay, so where are we right now? So first let me show you where are we right now. So we are learning parallel mathematics, that's required for machine learning and deep learning, and we also learned about programming. Okay, and now we have this machine learning and then deep learning part. Okay, and this is where we are at right now. So we have done something with the mathematics and then we have done programming, but in the programming we were at libraries. So we're learning about different libraries like NumPy, and then before pandas I thought first you should have a good glance of machine learning. Why are we doing it? Because we'll have to answer a question why for ourselves. Okay, if I am doing a machine learning course, okay, probably professor or the people who are teaching you, so they are maybe covering a lot of stuff. So first, in order to tell you where that stuff fits in, so you should have a clear picture. So for this lab, before going to the pandas library, so we should at least have some vision of what machine learning is. Okay, in machine learning, what are the things that are necessary and what are the steps that are taken, and these terminology you should be quite familiar with. And after that we'll again go back to pandas mathematics and then slowly come back as we are going like parallelly. We're learning parallelly machine learning, parallelly programming, and we're opening new subject of machine learning where we'll also take parallel lectures. So this is just some background I wanted to give so that you also do not feel lost. It's like maybe navigating a map, and you want to reach a destination, but in the destination you also want to explore different things so that you understand the journey better. So that's why we're parallelized and we're parallelly doing a lot of stuff, and that will give you basically the whole global view of the map. Okay, this is how the map looks like. Okay, and for this now let's move to machine learning. So if you see where this machine learning started from, so people when they saw themselves, let's suppose you see yourself, you ask a question to yourself, how do I learn, or how do the people around me learn? Okay, that's a fundamental question which people ask themselves. Let's suppose you see many of you are married, some people are going to get married, then you will have kids, and then you are amazed by the way how kid learns. Okay, and that's why we wanted to create machines which can think. So we call this process a thinking process. Okay, so thinking may have different definitions depending on different people. So this desire of creating machines who can think like humans or who can act like humans at least in certain ways, so it dates back to Greece, ancient Greece. So and they have some mythical figures in which they try to, okay, these are the figures which can think, and there are different inventors. We will have a separate history class on what is the history of this machine learning. But I want you to focus on this point. That our motivation of this was we were seeing humans all around, and we were seeing that there are kids are when kids get born, and then we have these people and they literally know nothing about the world, and then they slowly learn about something, and we don't know how they learn. Okay, do they learn because they see people, they see things repeatedly, they see people repeatedly? Okay, that was the curiosity humans had. Okay, can we made machines think? Okay, that was the first motivation people had, looking at the world around yourself, and then we were in that awe of that world. Okay, how is it so that we can do this? We can, if somebody speaks something, and you can from the voice even you can recognize this is that person. If you just look at an image, okay, and you can just picturize. Probably, let's suppose you see an image of me somewhere, you can say, oh, that's Musa sir, or that's Musa bhaiya, whatever you call me. And if you, let's suppose, see an image of cat, dog, you can directly identify this is a cat, this is a dog. That's one of that's one of the mechanisms we have. Okay, then first what we did is we said, can we formalize these things? Okay, the first thing I said is the word formalized. Today's session will be a mix of philosophy and the tech. So you should be asking me a lot of questions so that if I said a term which you don't understand, or if you think otherwise, you should ask me so that we clarify it there. So what I said is, so we are in machine learning. So if you see in there, we have this learning term. So I'm trying to explain this learning. Okay, so I said the humans were in awe of this. Okay, how do humans learn? And from that, can we create such machines which can think like humans, or can we simulate somehow it? So the tasks that we saw initially that we were successful was Can we formalize things? Can we find a mechanism behind that? So the problem is like addition, subtraction, multiplication, maybe a differential calculus. So for that, what we had is we had a formal mechanism of deriving there. Okay, and we had a representation of the data. So initially we know there is data and we had to manipulate it. But for that, we had a representation. Let's suppose to talk about maths. We had these numbers. Let's suppose 2024, and then we could add it 1500. If you see, this is a representation of something. Okay, and then we had a mechanism of how to add it. We have a stepwise procedure of how to add it. Okay, and then we made these programmable computers. So because we have the formalism, we have the formal notion, we have an explanation of how do we do it. So we made what are called as programmable computers. Okay, from that onwards, we thought, okay, we made a programmable computer. Can it now evolve on its own? The big question was, can it evolve? If there is an evolution possible for the machines, if it, and that evolution should happen on its own, and it should make it think. Can something like that happen? So people named that as artificial intelligence. So we had intelligence, and then can we create it artificially? So one thing is natural. So let's suppose evolution happens naturally, and whatever the theory of evolution is, many people don't agree with that. That's a separate story for some other day. But if you see the process of evolution, so in that they say that initially we were single-celled organism, and even before that, if you see, so how this consciousness, how this intelligence got created, can somehow, okay, because now we have these formal rules, we taught these to machines. So if you let machines, whatever they are doing is let them do it. Can they evolve on their own? That was the question that people try to answer. Okay, and people solved a lot of problems by using these machines. Alan Turing had a paper, some paper like titled "Can Machines Think?" Okay, can these nuts and bolts think? There is a famous test called as Turing test also. So this is the background where the human curiosity got fueled. Okay, so can we make a machine that can do tasks like humans? So the first attempt was some tasks we can do. Let's suppose the tasks which are pretty brain tiring and which are pretty hard for humans. Let's suppose if I give you a 20-digit number and I'll give you I'll say, okay, divide it by 3-digit number. So it'll take you some time. But if you see these computers, they were really fast at doing this. And why was that? Because they had a formalism, because we introduced a formalism into these computers and they could do it. Okay, these hard tasks which humans felt hard, like performing some calculations, and let's suppose we also find hard if you, let's suppose, have to do a thing which machines find really easy, like these computational tasks. Computational tasks are very matrix multiplication, what are mathematical tasks we have. But there were other set of tasks which was really easy for humans. Okay, it was really easy for humans, and it was very hard for machines to do it. Let's suppose recognizing an image. It's really easy for humans. It needs no, usually we feel it needs no intelligence. Even if a guy, we call him dumb. Hey, this guy is dumb, why he doesn't understand. But still he could identify images. He could hear the sound, or he or she. And all these things which probably we take for granted. Okay, that's why they're called intuitive. Why are they called intuitive? Because we feel it's so common. We don't need a formalism to make other people understand this. If I have to tell you how the addition is done, let's suppose you kids are you are the kids from kindergarten, or maybe let's suppose some other class, and you don't know how to perform addition. So I can tell you a formal way. I'll tell you, okay, this do this step, and then you can do the addition. But I'll never explain you how to identify an image. Nobody has told you that. Nobody has even told you how does somebody sound. How does somebody sound like? You just hear it and you somehow register that into your brain. Let's say I'm speaking right now. If there is a person who has not even who has not camera on, if he or she hears my voice, so he or she will be easily able to identify this guy speaking. This has never been taught to you. See how amazing this is. And this was the sense, and we wanted to basically solve these intuitive problems which we cannot formulate, which we don't have a formal method for, where we cannot where we cannot hardly have these set of rules. Okay, so now if you see the classical programming, the first distinction I'll make is like this. So you want to do certain thing. Let's suppose you have a task at hand. You have to do some task. So what do we do is you basically take data, okay, and then write a program. Okay, data and the program, and what happens when this data and program they run combined, they'll give you an output, the output that you want. This is the task that you want to perform. Okay, that's the formal sense. Here the thing is that this program contains that formalism. So this contains a formal procedure. You have to do this, then you have to do this, then you have to do this, and you land at the output that you want. Basically, we want to get from input to the output, or maybe data to the output, whatever it is. Okay. So if you want to go to the input to the output, so traditional programming is that you will write a set of instructions, which we'll call a program, which will take your input to the output. That's how these traditional things were. But now the point was, we don't know formalism. There are so many things which we can't formalize. Let's suppose we don't know a formal method of how do we identify an image. Okay, it's so complex for us to formalize it, but we can do it. Okay, so now the task of machine learning was like this. So you have, let's suppose, this data, you have these inputs, okay, and you also have these outputs. Okay, sometimes you have these outputs. So can you somehow find a procedure? Can you somehow find a mechanism? Okay, you'll feed this input and the outputs to that mechanism, and it should come up with these rules, come up with the program. Okay, then this program, once fed inputs, it will give outputs. Okay, so I'll maybe write it in different colors. So what you are doing is you are feeding inputs as well as outputs, and in some ways you don't feed the output. So I'm just giving a very bare bone basic example. So now the task of machine learning was, because what we were so maybe rookie or naive at this, that we couldn't find a set of rules or a set of formalism to identify an image. So what we did is we said, okay, can we do this thing? Can we just show inputs and the corresponding outputs to some machine and tell machine, okay, see, this is an input and this is an output. Can you somehow generate a program, generate a mechanism for me? Probably it may be a black box for me. So if I give this mechanism, this new thing, some input, and it should generate the output. That's how we thought humans learn. Okay, humans learn these intuitive tasks from how they observe the world. Okay, we have a setup in the world. So when we have a small human, small baby, so what they take a lot of information inside their brains. Okay, they create somehow some abstraction, some representation into their head. Okay, after that, basically, they somehow come up with this program, and once they see it, next time they'll tell you what this is. Okay, show just a few images of cats and dogs to a human, and after a while they should be able to recognize everything. So it tells us basically there are some things going in the brain which makes this program. So if you just compare the traditional programming, in traditional program what we have, basically we had these inputs and we write the program. So that was our program, was this. Okay, and then it was giving us the output. Okay, the intelligence was right here. Okay, we were trying to formalize it. We were trying to formalize it, and once we did it and we got the outputs that was intended for the inputs. Okay, this is the traditional approach. If I write this, so this is traditional approach. Why I call it traditional? Because that's how we learn a task. Because you understand the formalism. Once you have that formalism, you give an input and then you get an output from the formalism. This is what the machine learning is in a broader way. Because now some tasks are so complex to formalize, but they're so easy for humans. They're so easy for humans to do. Maybe even for the dogs and cats and even the lower mammals. So it is so easy for these entities to do. We can't formalize it. So we said, okay, can we do this thing? Can we somehow have a machine? I'll feed it inputs and outputs. I'll tell it, okay, look for this program somehow. So once I have that program, okay, I'll give you the input and then give me the next output. How many of you are understanding so far? Everybody? Any questions? So now this was the paradigm that we set, that we have a traditional programming and then we had machine learning, or we call it in general artificial AI. Okay, we generally call it AI. So this was the domain AI, and it has undergone a lot of name changes. People call it AI, artificial intelligence. Then some funding stopped, and we'll see all of that in the history class that I'm telling you that we'll take a separate class of the history. So what in early days of AI, what happened is, so a well-known program by IBM, that's called IBM's Deep Blue. So IBM's Deep Blue. Okay, it was a program so which defeated the famous chess player. Okay, it was a champion. His name was Gary Kasparov. In 1997, he lost against this IBM's Deep Blue. So this was basically, here if you see, chess has a world. Okay, if I tell you what is chess, so in chess there are these 64 boxes. Okay, and there are some pieces and there are certain rules to play it. and and a player comes up with different strategies. Okay, this is a simplistic world. So that is what this Deep Blue did. So Deep Blue somehow found really great strategies and came up with that. Okay, that was the first like attempt to the AI, and where it succeeded. Okay, before to this, prior to this, people thought, okay, can we come up with rules? Can we come up with some rules so that we can make the machines independent? So what they did is, there was a project called as CYC, CYC. Okay, so this project was there, and it was given a lot of what's called as knowledge base. Okay, it was given a knowledge base was given to it, and then there were some formal rules, and there were principles of logic given to it, and from that it used to infer the things. If you tell it something, if you tell this program something, and it used to give certain inferences from that. So, but it really struggled in a lot of things, because there were very less formal rules. It was not enough to completely explain the world. So there was a famous thing, and it was called as, like, it was given a story called as Fred is shaving his beard or something. So what it did is, it said Fred, while shaving, it considered it as, because it understood from the knowledge base that humans do not have electrical parts. Okay, but when it was given the story, Fred is shaving his beard or whatever, it considered Fred while shaving as one sentence, and it thought that it is some his Fred is holding an electrical razor. It believed that it is an electrical machine. Okay, something like that. So, and it did, these things did not have success when we came up with these formal rules and give them knowledge base. And still there are people who are working on what's called as formal methods, and there are something called as formal methods of software engineering. Okay, they said, okay, can we write some formal methods by the help of which we can at least like come up with the programs. So this was the first attempt, this SICK. And then came the IBM's Deep Blue, where it has a little bit of success. Okay, in which it won against a famous player of the time. Okay, so this was a little bit of like how it started all. Okay, and then the problem now was, in the machine learning algorithms, what you have is, the challenge of these systems was, you had this hard coded knowledge. Okay, hard coded knowledge basically mean, if you have a knowledge, you want to extract patterns out of it, out of this. These patterns are basically these programs. Okay, so somehow what you have to do is, you have to do this, and you have to make a machine capable of this, capable of extracting this information, so that what we can do is, we can extract these patterns from it. So people, what they do is, they came up with some statistical methods. Okay, what are called as statistical methods. They came up with these methods, okay, which were based on statistics and probabilistic methods. They came up with this, and what you do there is, so in these statistical and probabilistic methods, so you will take this data, okay, you will featureize it, and you will have certain features of this, and you will feed it to these algorithms. I'll just give an example of some algorithm. Let's suppose logistic regression. Okay, logistic regression is there. So logistic, and there is, let's suppose, naive Bayes algorithm. Don't be scared about these names if you haven't heard about these. They're very simplistic algorithms. They are based on probability and status. Okay, and this is, if you see, machine learning is just magnified statistics and probability. Okay, so logistic, if you see, let's suppose, if you have to see, there's a famous example. If you have to detect, let's suppose, if a lady is pregnant, and you want to see, will she give a normal birth to a child, normal delivery, or a cesarean is needed, or do you need to perform cesarean. So based on these reports, what you cannot directly give the image. You cannot now say, okay, I'll have an image of, let's suppose, the lady, and I'll say, okay, you need a cesarean. So doctor doesn't go like this. Doctor has certain parameters. Okay, let's check, does that lady has some uterine scars or something. Okay, and these are the features, and we look at these things. Okay, how was the if she has previously given birth to the child, and what happened that time. So doctor, he or she sees all these parameters, and then decides whether to go for a cesarean or not, or do you want to have a normal delivery. Okay, that's what these things are. What you can do is, you can come up with these features. You can come up with these features and feed these to these algorithms, and what they'll do is, they'll tell you, let's suppose, this logic regression will tell you whether to perform this cesarean delivery or not. Okay, similarly, in the naive Bayes algorithm, you can make a spam filter. By spam filter, I mean, you can have your emails, and you might also be maybe you have experienced this in your life, that you get a lot of emails, and many of them are spam emails. So can we somehow build a spam filter, where I'll give an email, that filter should tell me if this email is spam or not. Okay, for that also you'll have to extract features. Okay, so that is where comes this importance of data representation. Okay, so I'll write importance of data representation. So now how you represent this data? Let's suppose, as I said in the previous example, I said if you have to see whether the patient needs cesarean delivery or not. So in that, you will look at the different features. But for that, those features to extract, you should have the domain expertise. Doctor knows what features to do, what features to take. Okay. So what you basically do is you will have those features, and after that, you'll perform an algorithm. But coming up with these features in itself is a hard task. Okay, so what features to take, what features to not take, that's again a very difficult task. Let's suppose in these logistic regression, and if you have a problem defined and you'll take certain problem, and you will see, okay, these are the features that are important, you will feed these features into the algorithm, and algorithm will tell you something. Okay, and by this I can tell you, let's suppose if you have Arabic numeral, if you have 1 2 3 4 plus 5 4 6 8, so this is representation of a number, this is again a representation of a number, you can easily add this. Now if I give you same number in Romans, okay, people say that it's really hard to perform these arithmetics on these Roman numerals. Data is similar, but the representation is different. So representation changed somehow. Okay, how can we manipulate data? So now you see how important is the representation. If you have a better representation, that means you can extract better information from it. Okay, that's why I wrote importance of data representation. How do you represent data is very important. Okay, in machine learning also it's very important, even in the brains of humans. It's really important how do we represent the data. So that's why some people, probably the representation that is in your brain and the representation that is in my brain, it can be entirely different. We never know how is the representation in your brain. Okay, that's why this is very important. So how do you represent data into your algorithms? Okay, so that becomes a very crucial step in any machine learning, for many AI tasks. Okay, so designing the right set of features. Okay, if you want to let's suppose identify speaker. Okay, I was giving you the example, if somebody hears my voice. So you can maybe say, okay, is speaker male or female? How much is the length of vocal cord, and something like providing these clues. Okay, then you can probably come up with the right set of features, and if you feed to the algorithm, so algorithm will come up with the maybe with the right prediction. Okay, this is who is speaking. And now, as I said, this coming up with these features is really hard. So what we shifted to what's called as representational learning. Okay, this was machine learning. So machine learning somehow is a magnified statistical things and probabilistic things. So you have statistics. Sometimes I tell quite often to this to people that you can do these things by hand. You can perform logistic regression, linear regression, naive Bayes by hand. But what machines do it, they make it faster. Okay, and they perform calculation at very faster pace. Otherwise, you could have done it by your hand. You could have said, okay, I'll write some things, now give me next 20 data, I'll perform these calculations by hand, and I'll tell you what this is. Okay, so this is magnified statistics and probability, and we come up with the machine learning. Now the problem you saw is that data representation is very important. So we shifted to what is called as representational learning. Okay, so what is this representational learning? Okay, now the challenge that we faced, and we have to come up with these features. So now the solution was in this representation, where what we do is we have these AI systems. Okay, we have these AI systems who learn both mapping from the data and appropriately create its representation. Okay, they learn the representation. Okay, and then basically you give them data, so they'll somehow change its representation and give you the features. And the famous example is what's called as autoencoders. Okay, you give them some data, what they'll do is they'll encode this data into some lower dimension representation, into some representation. You probably won't understand it. If you are shown the representation, it won't make sense to a human. But that's their world. So they make this representation somehow, and after that you can whatever you want to do with the representation, you can do that. Okay, so there is a term called as separating factors of variation. That's what representation basically means. So what we are up to is we have to separate what are called as factors of variation. Factors of variation. So what is the meaning of this term, factors of variation? So the goal of representational learning is to basically design features. So you have to design such features. But now what you can do is, so you have to find those factors which give a lot of variety. Okay, which give a lot of variety. As I said, let's suppose if you give features who do not add much to the information. If you, let's suppose, give me somebody's weight, and let's suppose somebody's height. Somehow if you see, if you can give me somebody's height and somebody's height and weight, somehow these two things are correlated. So what we want to have is we want to have those features which has more variety. Okay, so which will make my task really easy to do it. Okay, so that's what I call as factors of variety. That's what this representation learning does. So it tries to come up with these separate factors of variety, factors of variation rather. And now the problem in that is in the representation. That was the problem in representation learning. So if you give it an image of, let's suppose, car, now what happens is it will give a representation of the car. Now you know that in the real world scenarios, car can be at different places. Let's suppose car will have different shadow and maybe a different lighting or something, like car may be in the dark, present in the dark. So same car, okay, will look a bit different, okay, in the different conditions. So this representation learning will form a different representation for that. If you give it a car, let's suppose, which is in the daylight, which has color red and something, those red pixels in the night will look like black. Okay, this representation learning has hard time to do that. Okay, that was the problem with with this representation learning. That is where we came with the deep learning. Okay, now after that we came with deep learning. Okay, most of people when they teach deep learning, machine learning, they say this is subset of this, this is subset of this. But I wanted to tell you, okay, how was the basically why did we come up with these things? So you see this. So we were with these mathematical what we call right now machine learning. We just had to curate some features, and then we'll use these applied statistics and probability, and we'll come up with some models like logistic regression, linear regression, or naive Bayes, and we'll feed it and we'll get a prediction. That was one of the ways. And then we said, no, coming up with the representation is pretty hard. So it's very hard to come there with a representation also. So can we somehow do one thing? Can we have this representation learning where we can learn the representation by the algorithm itself? But then I told you there is also a limitation to it, as I gave example of the car. So if car is in the two different same car, it can be under different lighting conditions. So representation learning will learn a different representation, other thing. But in actuality, if you see humans don't do that. Let's suppose you see a car in the dark, you'll identify it. Let's suppose if it's a Swift Desire, if it's a Baleno, whatever it is. So if you see this in let's suppose daylight, you can identify it as the same car. Okay, that's how humans have. So from this, now what we came up with is we said, now let's go to the deep learning. Why is it called deep learning? So in that we said we'll create layers of representations. So we'll start with maybe smaller some sub-layer representations that we probably, let's suppose if we have to identify an image. So initially we'll maybe, let's suppose we are doing this. Let's suppose I want to identify these handwritten digits. So what I can do is I can maybe first identify these smaller pieces, corners. Maybe I can first identify corners, something like that. Okay, then maybe I can identify some straight lines. Okay, then I can identify some circles. Okay, and these are different representations at different layers. Let's suppose what we are doing is we are learning it layer wise. We are trying to think that initially, let's suppose we'll have these input pixels, and then the first layer, let's suppose, will detect edges or corners, whatever you call. Let's suppose we'll detect edges, and then we can detect corners, and then we can detect contours, then we can detect some and different parts, so as to fully finally sort of identify this object. So let's suppose I'll again make this hierarchy. If you have an image or something, so let's suppose first we'll detect edges. Where are the edges? Okay, after we have this edge, we'll say, okay, now we'll let's suppose define what are called as contours. Contours are these basically what I wrote circles here. Okay, so after you have these contours, then we'll write different parts of the object, some parts, because edges form these contours, contours form these parts, and these parts form the whole object. So now we'll have we'll have different levels. Okay, different levels will give us the idea. Okay, we started from edges, so edges combined they form these contours, contours combined they form the parts, parts combined and they form the objects. Okay, that's what we assume deep learning is doing, and it's not sure that it is doing so. There are different parties which do believe in this theory. Okay, probably at different layers it is doing this, and this edge is the thing that we understand as humans. Okay, they're the edge, and contours as humans we understand they're these circular parts and these things, but maybe it's entirely doing different step. But the theory is that at each step, at each depth level, it is probably learning some lower level representation. Okay, as we humans think, let's suppose if you have to form a book, so from the book you will start with the letters. Letters will form words, words will form sentences, sentences will form paragraphs, and paragraphs will form as chapters and stories, and then you will have a complete book. So this is our way of thinking. Maybe machines think the different, but if you see underlying concept is that we are learning in the layers. That is the underlying concept. Underlying concept is you have some entity which let's call it, let's suppose A. Then with these A's we create B's, with these B's we create C's, with these C's we create D's, and this D is the thing that's our goal. Okay, now from our perspective, let's suppose considering an image, this A is an edge, so we are seeing edges, and from edges we create contours, from contours we create these parts. From these parts, we create a whole object. That's our way of looking at the problem. But maybe these networks, what we call as deep neural networks, that's why they're called deep. Why are they called deep? Because there are different layers. Okay. But the thing was that we'll learn the things, we'll learn things piecewise. We'll learn a piece of data once, and then we'll learn piece of data next time. We'll learn piece of data. That's what we call it. They're called hierarchical. There is a hierarchical composition. Hierarchical composition. Whatever the spelling is, I'm really bad at spellings. So hierarchical composition basically means at different hierarchy, at different levels. So different things are being learned by this. Okay. So now I said there are different ways to look at it. The two famous approaches which people call is, one is called as computational depth. Okay, the number of layers processing, and second is called as probabilistic model depth. So we'll see these things in detail, but I sort of wanted to give you the broad level vision. So how we came up with the deep learning. We said, can we somehow come up with this? And now that comes with that famous graph where people say this is AI. Okay, I hate that graph, but anyways, but that graph is right. Okay, it's not that that graph is wrong. Whatever, if I hate this graph, doesn't matter. So initially what we have is, so we have this AI. We wanted to make some system smart. Okay, we wanted to have we wanted to make something artificial intelligent. So what we said is, we said now it is a huge goal. What we can do is, can we come up with these probabilistic methods? Can we come up with these statistical methods where we'll have these features, where we'll have these features, and we'll do that. So we came up with machine learning. Okay, so we came up with machine learning, these things, and after that we came up with representational learnings. But I just wanted to differentiate between AI, ML, and deep learning. So after that we came up with the deep learning. Okay, so if I see in the broader context, AI engulfs everything. You basically wanted to mimic human intelligence, but you wanted to mimic it artificially. That's why it's called as artificial intelligence. Okay. Second thing was term machine learning. So machine learning has its in-depth roots in mathematics, like in statistics and probability. If you use that on steroids, you use computers for the computation, and then you do a certain type of feature engineering, you get these machine learning algorithms. Okay. Now I also told you the problem. From that we came up with representational learning. And representational learning also had its problems, okay, because as I gave the example of the car, then we had to come with the deep learning. The assumption in the deep learning is that in each layer we somehow learn some parts of the data, and then we put these parts together. If I have to identify an image, it's difficult to come up with the rules. So better part is, can we somehow learn at different levels? I learn different parts of these features, and maybe at the end that's how it's combining these features together. But as I said, this is our way of looking at the world. Maybe machine learning algorithm has different way of learning. These deep learning algorithms have different way of seeing the things. Let's suppose if you see a face of the human, you see a nose, you probably see my beard, you see eyebrows, you see eyes, and you see skin, and that's how you segment it. But what if maybe, let's suppose, other beings, let's suppose other mammals, or whoever sees you, they don't segment you like this. Okay, they consider, let's suppose, nose and the ear as one part. They consider one eye and eyebrow as one part. They segment people like this, let's suppose. Maybe their vision is like that. Okay, but if you see humans, they segment things differently, and how machines segment it can be entirely different, and it depends on the representation. That's why I came up with data representation. The same thing can have different representations. Okay, I'll call this is a pen. Okay, if this is a pen, whatever representation is in your head, I have no idea. How do you know this is a pen? But the thing is that reality is similar. You are calling it a pen, I am also calling it a pen. Maybe representation in my head is different, representation in your head is entirely different. Similar with the colors. If somebody says that is green, okay, maybe that green looks something different to you. There is no way of me telling, okay, this is green. What is the representation in your brain? Okay, you can say this is green. Maybe we agree on the point. We agree on this point that green looks, this is green. So if I say, let's suppose something is green, you have entirely different representation, and somebody has a different representation of that in the brain. Okay, but still you come on the same consensus that this is green. Probably green to you looks red in the head. Whatever representation of you have of the green, I might have the representation for the red. But once somebody is told, what is this? So he'll say it's green. Okay, but the representation can be entirely different. Okay, now again summarizing it. So AI basically has a goal that will somehow mimic intelligence, and will try to artificially create it. And whatever you see being intelligent, you can call it AI. And then we said ML. We have this data. So now we'll crush this data into these statistical and probabilistic algorithms, and have these features done, and we'll feed these algorithms. And these algorithms will somehow come up with these patterns. They'll say, okay, this is the patterns I'm finding. That's what we call as machine learning. And now the machine learning had the problem, we had to curate features. And now in order to create those features, sometimes it's really hard. It's really hard to come up with the features. So we said, okay, can we come up with something which is called a representational learning, which will just learn the representation itself. But then representation learning has a problem. The problem is that if you, let's suppose in this for the same thing in different scenarios, it has different representations. As I gave the example of car, the other example can be, let's suppose, speech. Okay, speech. Let's suppose we gave male vocal length is this much, but still it will come up with the different representations. Okay, and now we came up with the deep learning, which says that we'll learn the information layer wise, that's piece wise, at each layer, at each depth of the layers. Can we learn some parts are these, and then we'll put them combinedly, and that's why we call it deep learning, because deep means it has depth, and learning it learns, and everything has a learning in it except the artificial intelligence. And intelligence, the create was to artificially come up with the methods of intelligence. Okay, there is a huge debate going on. What is intelligence? What is consciousness? And all these things are coming up. Okay, so within that deep learning, now we have the generative AI. So if you understood these terms, then you at least are going in the right way, because we'll be using these terms everywhere. Okay, how many of you understood these things? Any questions on this? To just summarize what we have seen so far, what I'll do is I'll make a diagram. So that's what we said. We initially said we had the rule-based systems. So what we had rule-based systems. I'll try to write as good as possible. Okay, so in the rule-based systems, what we have is we had these inputs. Okay, we had a block of inputs like this. So this was our inputs. Okay, these inputs were fed to these hand design programs. Okay, we had these hand design programs. Hand design programs, and then they gave us outputs. Okay, that was one way of learning. Then we had classical machine learning. Okay, in the machine learning, what we said is we said that we gave inputs and then we gave high level hand design features. Okay, we gave features rather, and now what we did is we had these inputs. I should make it a little better. So we had these inputs. So what we did is we made hand design features. Hand designed features. So I'll write hand designed features like this, and here I'll also write hand designed programs. So otherwise this will hand design programs. Okay, so from this the output was a mapping from these features. So we learned a mapping of these inputs to the outputs. So what we learned a mapping. Okay, we learned a mapping to the output. Okay, so this is what we learned. So what was it? This was our classical machine learning. I already call it classical machine learning. And then we came for the representational learning. In the representational learning, what we did is we had input and we learned features, and from these features we learned mappings. Okay, so I'll color these things. So inputs and these things were learned. This mapping was learned. So here basically nothing was learned. So here if you see mappings were learned. Okay, from these hand designed features to the outputs, these mappings were learned. I'll just maybe draw a border or something for the learnings, where learnings happened. Okay, then the representational, what happened? We had same inputs. Okay, we had these again the inputs. So in the inputs now we did not have hand design features. We learned these features. So we have learned features. I'll call them learned features. Okay, this is, I'll create a border out of this, so because they are learned. Okay, and after this learned features, now it also learned mapping. Now we also learned mapping of these features. So we learned mapping of features to what? Mapping of features to output. This is again what we learned. We learned this also. Okay, this was our representational learning. Okay, now we had a more concept, that is deep learning. So in deep learning, what we had inputs, then we learned simple features. Okay, from the simple features we learned additional complex features, and then we learned mapping. That's why it's called deep. There are different layers. Okay, so deep learning also can be thought as a representation. It's a type of representational learning, but a representation in many layers. So this is our input. And then we learned simple features. Simple features. I'll call simple F. And then we learned more complex features, or maybe I call them higher level features. Okay, higher level features. Okay, and then we learned a lot of higher level features, and at the end we learned mapping of these features to output. Mapping to output. Okay, so these things are learned. So this, oops. So this thing is learned. This thing is also learned, and this thing is also learned. And here can be a lot of layers. Okay, so this is our deep learning approach. So this is deep learning. So what I said is, I said deep learning is also a representational learning. But in representational learning, we generally just learn the features and done. We're done with that. But in deep learning, we have layers of representations. We have different layers of representation. And initially, we have some low levels of representation. Then when we have some higher level representation by the additional layers, and we keep on adding these representations, at the end we learn the mappings. For how many of you is this clear? Okay, this diagram is basically taken from a really famous book called as Deep Learning by Eon Goodfellow and Yeshua Bengio. So Eon Goodfellow. Credits to these people. So he was the one who came up with these GAN models. Okay, and Yeshua Bengio, if you know the guy, he is one of the pioneers of the field of deep learning. So they have written a book on deep learning, and that's how they have explained in the book itself. Okay? Any questions on this? And then we'll see, basically these things are just name mimics. So if you see now deep learning, AI, it has actually a lot of name changes happened. So there has been a lot of name changes. Why did this name change happen? I'll just tell you a brief story, how the research works. Okay, just a little bit digression. So people just came up with the AI system. They said, we can do this and that, and they overpromised the stuff. They said we can do this and that, and we can make humans like machines, which can think like humans, talk like humans, do everything like humans. And they promised, and there was a huge hype around that. And then some set of people, sometimes scientists, they came up with, they basically proposed what are called as perceptrons. So perceptrons were which hyped this field of machine learning. So now what happened, because that some people came, they said, okay, can you just map this XOR function in perceptrons? A single perceptron cannot map XOR function. So they said, if you cannot map XOR function, how are you promising these things that will be able to make a machine, it speaks like humans, thinks like humans, walks, everything like humans? So how will you do that? So because of that, now funding stopped in AI. And nobody thought about it. People thought this AI is dead. Now people should not research about this. So that's called as AI winter. Okay, by AI winter, they mean that almost the very less research was done in that area at that time. And after that, like some people still were doing, and they came up with multi-layer perceptrons, and then huge amounts of data came, and then the resources came. There are three reasons which I will briefly discuss. And after that, again, this there were a lot of name changes that happened. Initially, it was called as cybernetics, then it was called as connectionism, and then it was called as artificial neural network, then machine learning, deep learning. Different name changes happened because of whole of these gimmicks. Okay, and it's a famous saying that I think before some 25 years, if there was a paper submitted which had machine learning or something in it, and they had the highest rate of rejections. Okay, because people thought these people are over-promising, it's better to reject these papers. Now, if you see, more the papers are coming in machine learning. Okay, that's how research goes. The funding goes there where people promise a lot of stuff. And after AI winter, I think it took off. This machine learning deep learning, it took off after 2012. After what's called as AlexNet, that CNN challenge, convolutional neural networks was born, and then people thought actually it has power, and then rest is history. Now you are seeing large language models. In 2021, GPT came, and a lot of stuff came, and then people are now going nuts around this machine learning and deep learning. I think somebody has a question. Yes. Now you saw how we came from machine learning to deep learning to this generative AI and stuff like that. And now what we'll do is we'll formally see what is actually the meaning of the learning. Okay, what does it mean to learn? Okay, so we are in this learning, machine learning. So machines, you understand what is a machine. There is a huge definition of what machine is, but we are more interested in learning part. Okay, what learning is. Okay, there are formal definitions for these learnings. Okay, what these learnings are, there are definitions. So Tom Mitchell, I guess his name is Tom Mitchell, he gave a definition of this. So I'll scare you with the definition, and then we'll take it part by part. So what he said is, he said a computer program is said to learn from an experience E with respect to some class of tasks T. Okay, I'll write it rather. I'll also read it from something. So a computer program is said to learn from experience E, is said to learn from experience E. I'll capitalize these letters so that it is visible, with respect to some class of tasks. With I'll write with respect to like this. So with respect to uh, some class of tasks T. I'm again capitalizing this. So what he said is a computer program is said to learn from experience E with respect to some class of tasks, let's call them T. So and the performance measure P, and performance measure P. Performance measure P. So this is how we'll measure the performance. Okay. Now what if you see, these are three important things. Okay, so computer is learning with experience. Okay, learning what? Learning some task. Okay, so how are we quantifying that learning? We're quantifying that by if it is performing better. Okay, now what we'll say is, so that's the second part of the definition. Now the second part comes. Initially we set up the thing. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure P. Okay, these are the things. So now what he'll say is, he'll say if this performance increases on this task with, by having more experience. Okay, that will put it now in the words. So what is he saying? So now the second part of the definition goes like this. So if its performance, that is P, increases, so it should increase. If its performance at task T, okay, increases as measured by P, okay, and its performance increases with at task T with experience. So I'll also write that if its performance P at task T improves with experience, improves or increases, improves with experience E, as measured by P, okay. So these are things. So again I'll tell you there are three important terms. One is experience, okay, one is task, and one is performance. Okay, what is performance? We'll come to that separate. We'll take everything one by one. And what's XP? What is task? So the first thing is there is something that you want to perform, and you're performing that task. Task, let's suppose, is eating. If you want to eat, so that if you want to eat from a plate and you have never eaten from that plate, what will happen is, now I'll measure that thing. Let's suppose by how much food do you spill. That is my performance measure. I'm measuring your performance. And let's suppose you are eating rice. So how many of these grains will you spill? So if you spill more grains, your performance is less. So what I'm saying is, with each experience, like the more you eat it, okay, with the experience, and because the more you do it, I assume that you will spill less of this rice if you are eating that. The task is eating rice, okay, and experience is if you do it couple of times, and P is the performance. What is the measurement by which I measure your performance? How well are you performing? So I said in terms of this eating rice, I'm saying how less do you spell. The less you spell, the good you are performing. So what I'm saying is, so if you with experience E, okay, with experience E, if it's performance P, so your performance P at the task T, it improves with experience E as measured by P. So how many of you at least got an intuitive understanding of this definition? What is definition saying? Okay, so it says if you are performing any task T and with experience E as measured by the performance factor P, it should somehow improve. Okay, now we'll take each of these terms one by one. We'll take what a task is. First, we'll see what a task is. Okay, what is a task? Now, this is the definition of learning. Okay, this is what definition of learning, and this is given by Tom Mitchell. Okay, Tom Mitchell gave this definition. So now we are dissecting this definition. So first we'll see what is a task. Okay, so machines, if you see, now the thing that we want them to do is to basically learn some pattern, as we said. That learning pattern might be a task. Okay, let's suppose it might have different philosophical point of views, but here I'll try to keep it simplistic so that everybody learns it, because it's a relative term for the task. If I say okay, but is food eating a task? Okay, if you learn its formal algorithm, you will say, no, I learned the algorithm, but I did not learn the task. Okay, you rather learn the algorithm. Okay, so I'll say what task basically is. So task in any machine learning usually is described how this machine learning basically learns, the process of learning. Okay, the process of processing that example may be called a task. So there are different tasks. I'll just give with the examples. I'll make it clear. So one task can be task of classification. So classification. This is a task. So in classification, what your program is, you have a specified program, and let's suppose you have k categories. You have some k categories. So in this, what I mean by this k categories, I mean, let's suppose you want to classify something. You have, I'm making circular definitions. So let's suppose we have, as we took the examples, we have plants, and we have 4 types of plants: setosa, versicolor, virginica, and something else. Okay, and some setosa, versicolor, virginica, some ABC, let's suppose. And these are 4 categories, let's suppose. I forgot one more category. So these are 4 categories of these flowers. So now my task is given the features of these plants. How can I classify these? Okay, what type of flower is this? So if I write it mathematically, so f is a function then. So f is a function which takes, let's suppose, Rn. Rn basically, it takes a real number values which has n dimension, n cross 1. It takes a vector of n numbers, and what it gives is, it gives an output, some number from 1 to k. That's k classes. So this is what I can call as classification in mathematics. So classification is, this f is an algorithm or a class. This is the task of classification, where we take a n real valued vector. Okay, R of n. That is how I wrote it, and it gives one of the k classes. Okay, everybody with me for this? Okay, I give an example of classifying, let's suppose, these 4 types of flowers, and classification task can be, we'll have a classification task, let's suppose, for handwritten digits. We have 10 numbers, and we want to recognize the 10 number of digits. We want to classify it, that this is one of the tasks. Okay, so the other task can be, let's suppose, classification with missing values. Okay, classification, we have a challenge in that. So in that, this classification will have the Rn vector. Now classification can be like this. So where we have the missing values, classification with missing values. Okay, this is again a task. So you'll be given a task, but all the values won't, all these features won't have the values. Some values will be missing. Okay, so you'll have to have a way so that you learn these different classes from these. This is again a task. Okay, in this classification you can have binary classification, multi-level classification, but I'm just saying what kind of different classes can be. One classification is where all these features have values, but there are certain ways where there are missing values, because you know that how when data is collected, the problem in at that time is because of human error or because of non-available data, because of the malfunction of devices, you can get missing values of these features. So at that time, what should be done is, you have to handle these missing values, and you do classification with the missing values. Okay, that is, this can be called a subset of the classification. And the second problem is, one more task can be regression. Okay, what regression is? Now we don't have classes, we have continuous value, range of values. How is this? Let's suppose you want to predict height of people. Height of people is a continuous value. Or let's suppose you want to predict stock market prices, you want to predict housing prediction. So all these things are regression tasks, where when you are given a set of features, what will happen is you will get a range of value. Let's suppose I'll write it mathematically like this. So I'll say f takes value some Rn vector, that is, it takes n features, and it gives a real value. Okay, so this can be task, this is a regression task. Okay, so in this example can be stock market prediction, stock prediction. Okay, or height prediction. Anything that takes a continuous real value, I can call this is a regression task. Okay, then we can have a task at transcription. Okay, transcription can be a task. Okay, so what is this transcription? So let's suppose I can tell you like this. So machine learning is asked to observe some unstructured data. If it is giving an unstructured representation of some kind of data, so it is asked to transcribe it in some format. Let's say I have an image and I want to generate a caption. This is transcription. So I have an image, so I am telling you to give me the caption. And with you people, with some of you people who are doing a project that is transcribing notes. So what that basically is, that's again a transcription task. You are giving a video, or you are giving an audio file, you are giving some other thing, and you are from that, you are trying to, from that unstructured data, unstructured representation, and you are coming up with some representation, maybe in Unicode, ASCII, whatever it is. Okay, that's called as transcription. So I'll give an example, that is maybe node generation from videos, okay, or captioning, image captioning, that is a transcription task. Then we have machine translation. Machine translation is also a task. Machine translation, this needs no explanation. If it's a one language, you have to convert into other language. If it's English, you can convert into Hindi, Chinese, whatever, from the Chinese to the Hindi. This is machine translation, how we can convert one symbol type into another symbol type. Okay, that's called as machine translation. So if you see, machine translation again can be seen as a transcription also, because you can get some unstructured things and you generate some output out of it. It can be seen also like that. Then we have what I call as structured outputs. Okay, the structured outputs, I'll write it first. Then we have structured output. This is again a task. So structured output task, it involves the task where the output is a vector. So you have a whole vector as an output. Okay, so let's say, or maybe containing multiple values. Okay, let's suppose important relationship, and they have some relationship. Let's suppose you are generating some vector, but here these elements have some relationship. Okay, that's structured output. Let's suppose you are generating, how can it's an example, you want to annotate a sentence. Let's suppose we have a sentence, cat sat on the mat. Now structured output is, you want to annotate this, which is the verb, where is noun, where is the different thing. So we call it as a structured output. So you want to give a structure to this output. So that can be again a task. Okay, and after that we can have what's called as anomaly detection. This is again a task. So what is anomaly detection? Let's suppose you have some usual things. If something unusual happens, that's called anomaly. So you have an anomaly. Let's suppose in transactions, if you see above 99% transactions, these transactions are legit transactions. Okay, but some of them are fraud transactions. So fraud basically is an anomaly. So here we can say fraud detection. It is an anomaly problem. Fraud detection. So we are in the task, in that, and in the definition of task, what is a task? So I am giving you different things about the task. Okay, and these are things that machines have to learn. Then we have one more task, what is called as sampling and synthesis. Synthesis or sampling. Synthesis, sampling. Okay, if you want to synthesize something, let's suppose you want to generate new text, you want to generate new images, that we can call synthesize and sampling. Okay, so here generative AI. Now you don't need an example. Okay, you want to generate some text, you want to generate some image which is not there. So this is synthesis. Now you can have imputation of missing values also. There's a task called as imputation of missing values. Imputation of missing values. Why is it a task? Let's suppose you are given a sentence. Let's suppose a cat sat is not given on a mat. So what you have to now, you have to impute this, there is a missing value, you have to fill this missing value, you have to impute this. Imputation means you have to change it somewhere, you have to fill something in there. So this is an example of this imputation task. So you'll be given missing values and you will have to fit the missing value. So as you complete this. Sentence completion is one example of that. Okay, imputation of these missing values. And then you have something called as denoising. All these are tasks. Denoising. So denoising, basically, if you have a signal which is noisy signal and you want to make it a better, let's suppose you have image is blurred image, you want to create a good image out of that's called denoising. Okay, you take now noise out of it. And let's suppose you have some video and that video is very low quality, you want to make a high quality video. Okay, that is denoising. And the little definition of denoising, if you have a sound which contains a lot of noise, you remove the noise and get a good quality sound also. So this is also called as denoising. That's again a task. Okay, there are different tasks that I mentioned. And then we have something called as density estimation. Density estimation. So density estimation, or it's called a probability mass function estimation, PMF estimation. Because many things are probabilistic, we'll see that. So in here we want to estimate the density. Okay, so one example in that is, I can give you why we do density estimation. So let's suppose if you have a probability distribution, you think that these samples come from these distributions. So what you try to do is you try to estimate the density as a whole. It can be done in images, it can be done in generation of audios, because if you know that these images come from a particular distribution, okay, and you can just estimate the density, you can estimate density, and from the density you can come up with the new samples. Okay, these are at high level what these tasks, what I mean by tasks. So tasks can be, we started with classification, then classification can be classification with missing values, then we can have regression, we can have transcription, and we can have machine translation, structured outputs, anomaly detection, and synthesis and sampling, imputation on missing value, denoising, density estimation, and there are a lot more lists to do. But I think this is not an exhaust list, but I hope that you got a hang of what tasks mean in machine learning. Okay, can I assume this, that you understood what tasks mean in machine learning? So these will be the tasks. So now we have performance P. Now we'll come to performance. Performance P. Because now we saw that tasks T. So we said in machine learning we want to do these tasks T, and we are saying that we will measure the performance. Are you getting better? Is the machine learning algorithm getting better at this task? How will we quantify? We'll come up with a metric. Okay, this is a metric. This is a metric of performance. By that I mean how good is it performing? Is it badly? Is it poorly performing? Is it performing good or something like that? One simple can be error rate. Okay, error rate. How much errors is it making? Let's suppose if you are in the classification task, you are saying how much error is it making. From the error we get basically what's called as accuracy. Yeah, how much accurate is the model? So is it accurate? Is it something? And this is also actively seeked research area. Let's suppose in these large language models, you never know how better is the output. Okay, and then you come up with different scores. Okay, and these metrics will have to come up. How can I measure performance? Okay, so I said one of the things is accuracy. You can measure error rate. You can measure this accuracy, and there are different things which you can measure F1 score. You can measure recall, precision. Okay, recall, precision, and there is something called as area under curve. Okay, you can measure region, maybe something called as union or intersection, UIO. There are a lot of metrics that we come up with for the different tasks. We come with different metrics so that we say if this task is getting better, if it is performing better, if the performance is increasing or is improving. So accuracy is one that is very easy to understand. So let's suppose if you are doing a classification, binary classification is 0, 1, and what you are saying is by accuracy you mean total predictions, that is total predictions divided by correct predictions, correct divided by total predictions, or maybe total points. You have data points, let's suppose 100, and out of these 100 you got 90 of them accurate, so you are saying 90% is the accuracy. Okay, and error rate also you can also compute error rate from here. So then we have this F1 score which comes from this recall and precision. Then I said we have something called area under curve, we have this union or intersection, and there are a lot of other metrics, and we'll have a separate detailed discussion on what are different metrics to measure these performance of these models. But I hope that you at least got some hang of what is the meaning of this performance measure P. So this is performance measure P. This is a quantification. Quantification basically how well can you quantify that my model is at least performing. But because if you have no way of telling is it model performing good or not, then why do you work with the model? So this is the mathematical quantification of the physical realization of that. Then we have this experience E. Okay, now coming to the experience. Okay, I forget spellings. Experience E. Okay, what is this experience now? So in the machine learning, these tasks are maybe algorithms can be classified broadly into two categories. So the algorithms, I am now talking about the experience. So these algorithms can be classified into two categories. One is called as supervised learning, and there is called as unsupervised learning. There is something called as semi-supervised learning also, but I just wanted to give you a broad categorization. Supervised learning is the way where you learn basically under a supervision, because the word supervised is there. So what I mean by this is if you see data, let's suppose, in that data what you will have is you will have features, and if you have the output class also, let's take the example of classification. So you will have data and then you will have labels, corresponding labels. If you have data features and corresponding label given to you, and then you train a machine learning model onto this is called as supervised learning. Okay, so you have basically, so if I have data D like this, so each point will be x1 comma y1. So x1 is all the features. Okay, so x1 basically can be a vector of features. It can be like this, it can be x1 1, x1 2, x1 3, something like this. Okay, so I have x1 y1, x2 comma y2, and so on till xn comma yn. So this is my data set. Okay, so data set basically means I have these are my features. So this, they are my feature vectors, and these are my labels. So this and this, they are my labels. If my data set is given like this, I have features and the corresponding labels given to it, and I feed this into the machine learning algorithm. So in this setting, I call this a supervised learning algorithm. Okay, because I am giving the data set and I am also giving the corresponding labels to it. Okay, basically this is called labels, the class labels. Okay, these are my feature and these are my class labels. Okay, these are called as supervised algorithms. Supervised algorithms. So one experience can be this. You can learn in this sort of experience where you have a supervised algorithm. Then I said there is unsupervised algorithm. In unsupervised algorithm, you have this data set in which you just have been given like this x1, x2 till xn. You just have been given data and no classes are given to you. No class labels are given to you. You have to find classes. Let's suppose in here classification. I gave an example of classification. Okay, and here I can give example what's called as clustering. Okay, you want to form clusters. You form we form different clusters of this, and let's suppose if you want to see how many cancer patients are there, so you'll have image of let's suppose some will say, let's suppose we are detecting brain cancer, so we'll have images or scans of these brains, and now we don't have this labeled data. We don't have labels. So what we can do is we group the similar things together, and it will form some clusters like this. Some cluster will be formed like this, some cluster like this. We call, let's suppose this cluster is cancerous, this is not cancerous cluster. But here if you see, explicitly labels are not given to it. But from the algorithms, we learn the clustering. Okay, that is called as unsupervised learning. Okay, one I said is called supervised, and then we have unsupervised learning algorithm. Then we have some semi-supervised also, where some data points are labeled and some are not. Okay, one more important aspect that there is, that's called as reinforcement learning. Okay, we have reinforcement learning. So in this, basically what we have an agent. An agent is in the environment. So environment, and agent can be in the different states. So it takes its position from one state to other. It changes states, and there is a reward function associated with it. Okay, so it does what's called as exploration and exploitation. Exploration and exploitation. Exploitation. So what is the meaning of this? So if you let's suppose consider yourself into the reinforcement learning environment. So agent is, let's suppose agent wants to learn how to walk. Okay, there is an agent, and task is now you have to walk. Now what it does is it does different steps. Okay, can I walk like this? Can I walk like this? It performs different transitions and sees how stable, and there is a reward function associated with it. There is a reward function. Okay, this reinforcement learning comes from a mathematical construct that's called as MDPs, Markov decision processes, and we'll if we go there, we'll also learn about a bit of reinforcement learning. But here, if you see, there is an agent. Agent performs different actions. So agent performs actions, and action takes agent to the different states. Okay, and once this transition happens, there is some reward associated. It can be reward, negative reward, positive reward. So exploration means you explore different states. Okay, exploitation means whatever states gave you higher reward, you keep on doing those things. Okay, and there has to be a balance between exploration and exploitation. You have to exploit the things that give better reward, but you still have to explore other things. Otherwise, probably you will miss out on the state which will give you more reward. So that's why you have to balance out on this exploration and exploitation. So if you have an RL agent, usually call them RL agents. So RL agents, you have an agent, it has certain actions to perform, and these actions take it to certain states. Okay, again, with these states, there is an associated reward function. You give it a reward function. Okay, the famous I think case study you should everybody should watch. It's called AlphaGo. So AlphaGo is an RL agent. So AlphaGo, and with I think this was made by DeepMind. So AlphaGo, the Go is a game. So there's a documentary on this AlphaGo. So now if you see this ChatGPT, how are they trained? They're trained by what's called as RHLF, reinforcement learning by human feedback. So reinforcement learning by human feedback. Okay, by human feedback, they mean, let's suppose if you might even you do that right now, you do that. If you just prompt ChatGPT, if you prompt these models and they say, do you like this response? So it says yes, I do like this, and you basically again train it. And something what will happen is so some people are hired for this. They'll prompt a model, and if it gives a response, they'll say no, the response should have been like this actually, but you gave it wrong, so you should give it like this. So it continuously, because humans are now giving some feedback to this. So this is called as reinforcement learning with human feedback. So it adjusts its response next time because the human gave a feedback. So all in all, what we have is you have an agent performs certain actions. So actions take you to different states. Okay, and there is a reward function associated with how much reward do you get. Okay, and then you balance between this exploration and exploitation. That's called as reinforcement learning. So we saw at least 3 paradigms. And a broader level, we saw many categories. So first we saw supervised learning, we saw unsupervised, we saw semi-supervised learning, and we saw this reinforcement learning. What is supervised learning? When you are training an algorithm which takes the data as well as the corresponding labels. That's supervised learning. Then you have unsupervised learning, where you don't have supervision. You give the data only and you don't give the labels, corresponding labels. So that's called as unsupervised learning. Then you have semi-supervised learning. Semi-supervised basically means where some data is labeled, some is not. That's the typical case with medical data. Okay, and that's because some things are labeled, some are not labeled. So that's why you do the semi-supervised learning there. And even it's a typical case of fraud transactions also, where some transactions are labeled fraud and some are not labeled. Okay, and some are even some are labeled legit and some are not labeled legit, and there are some missing classes. So then the last part we saw is reinforcement. Why is it called reinforcement? Because it reinforces. Okay, if you see, it somehow takes a feedback and reinforces the thing. Okay, no, you should again take it. There is an agent takes an action takes it the state, and within that transition, a reward function is defined. It gives a certain reward. So if that reward is more, we try to do it more frequently. That's called as exploitation. But in the hope of this, that there will be states where we'll get much better reward than we are getting currently, and we try to explore also different things. That's called exploration. And there's a famous problem of exploration versus exploitation. So you have to balance between these things. Is it clear so far? Okay. Any questions on this? Any questions still here? Now what I'll do is I'll tell you a typical pipeline. So I'll tell you a typical pipeline of these ML or deep learning algorithms. Okay, when you have to perform something, there's a pipeline. By pipeline, I mean what are the different steps involved. Okay, and these can differ, but I'll give you a generic pipeline, which you will see in like at least more than 80% of the problems you'll use the same pipeline. Okay, pipeline or the set of steps. With that, we'll end today's session. So this might be the last topic. Okay, because we are approaching our limit time. So what is the typical pipeline looks like? So the first thing that we have is, I'll just make it maybe in the boxes. The first thing that we do is we define the problem. Okay, we have what's called as problem definition. So problem definition. So in the problem definition, what you basically do is you objectify your problem. So you have an MLDL task, any machine learning or deep learning task. So in this, what you try to do is you define the task. The task can be classification, the task can be regression, object detection, whatever it is. You basically define this task, and then you also define an objective of the task. So objective is understand the business and scientific objectives. What you want to basically achieve out of this. If it's a classification, what do you want to classify? If it's a regression task, what do you want to predict? If it's object detection, what kind of object do you want to detect? Okay, so you want to define the objective. So that is the problem definition. Okay, now once you have this problem definition clear, and once you get to know that I have a problem that's clear to me, now you will move to the second stage. So this is problem definition stage. Okay, this is problem definition. Now the second step after this is, now you have to collect data. So I'll make it with this color. So now what we have to do is there is a stage called as data collection. So in this, you have to first find sources. You have to find sources of data. Okay, I think you guys are doing some projects with me. So there we defined the problem first. We had a clear task that we want to do this. And then we had an objective of that. Okay, now our objective is this. And now we are in this mode of data collection. So in that, we find the sources. We gather all the relevant sources. Let's suppose databases, some sensors. We do web scraping. We use API calls, whatever we do. And then what we do is we format the data. By formatting, I mean we ensure that it is in the appropriate format. Let's suppose in CSVs, in JSONs, in images, and we do this. So we have problem defined. We have an MLDL task that we want to do, and that is the first thing. And then we have an objective defined. And then what we do is we do data collection. Okay, I should make it a little bit better. At least it looks beautiful. And after this, what we do is after we have the data collection, we move on to the next step. That is, now we have to process the data. Okay, we have to process this data. Okay, I'll write it here. So let us use some other color. So we do this is called as data pre-processing. Data pre-processing. This is a huge step also. Once this is here, it takes a lot of time, and here again you take some time. Then what you do is you basically do data pre-processing. In that, what you do is you do data cleaning. You have to clean the data. By cleaning, I mean you have to handle missing values. If there are, you have to remove duplicates. If there are inconsistencies in the data, you have to figure out that, and then you do what's called as feature engineering. Feature engineering. So in that, what you basically do is, so you create new features like how to handle these categorical variables, how to scale, how to normalize, okay? Scaling, normalization, that's all of it. And deep learning, if it's an image data, you have to resize things, you have to again normalize pixel values. If it's a natural language processing, then you have to tokenize data, and you all of these things, okay? And after this, after you do data cleaning, after you do feature engineering, then you split the data. By splitting, I mean what should be the test set, what should be the training set, what should be the validation set. You split it accordingly, splitting it into like training set, validation set, and test set. So what is training? The amount of data you give it. Let's suppose you give data and it trains, and then you test it on some data. Okay, how it is performing. You also give validation. We'll see what validation means, but you have to know these terms. So we'd split the data. After splitting, sometimes we feel no, our data is not much, so we should augment data. We also do what's called as data augmentation. So we add more data to it. Okay, we said let's somehow maybe augment it with some other synthetic data, or maybe if it's an image data, flip the image, maybe lower the brightness, do something so that you augment the data with something. Okay, these are the 4 steps that we do. So in the data preparation, data pre-processing rather. So in the data pre-processing, we clean the data, we do feature engineering. So in feature engineering, what we do is we create new features, okay, or do how to handle these categorical variables, if there is some inconsistency, how to remove duplicates, and all these things, how to handle missing values. So these things are done. Then we split it. What is the meaning of split? By split, I mean you have to have training set, test set, and validation set. So training is on which this will be the data where I'll train my model, and then I'll have to have a test set. Okay, I'll tell you the rationale behind that also shortly. Okay, and after that splitting, then if you feel no, my data is less, can you augment it? So rather you augment the data first, then you split. Okay, you see I have very less data, probably I should augment it. Okay, then what you do is you do what's called as model selection and model designing. Okay, after this phase, after this over here, so what you do is you do model design, or model selection. If already a model is designed and you just have to select models. So in this in this model selection, you say, okay, in let's suppose in machine learning, you will say I'll use decision trees, I'll use logistic regression, or some models I'll use. Or in deep learning, what you will do is you will say I'll use a particular model architecture. I'll define architecture. Let's suppose I'll use CNN, or I'll use RNN, I'll use transformers. Then I'll define these many layers of these I'll use. So you'll come with an architecture. Okay, that's why you will design this model, or you will select a model. By selection, I mean if you already have SVM, logistic regression, decision trees, these are the algorithms, you will directly use them. Otherwise, if you have to design this, you will have to design, okay, I usually use CNN with these many layers, with maybe let's suppose this kernel. If I have to use transformers, I'll use decoder only, encoder only transform block. So whatever you want to use, and that you have to design to over here. And then comes the model training part. Okay, from here we'll come to model training. Oops. Then comes this model training. Now I'll show you what's the basic meaning of this training, and then we have this evaluation also. So I'll say what is the meaning of training and testing first. Training and testing. Most of you will know, for the sake of completion I'll do it. So now you have a model. Let's suppose you have the design choices. What you give input your data, and then you get the corresponding output, and you continuously, let's suppose in deep learning, you optimize the parameters. And if it's an iterative algorithm, as in deep learning, in machine learning also, if it is, let's suppose, SGD based algorithm, so what you would basically do is you also update these parameters in logistic regression, linear regression, and things like that, and you do it on certain data. So your data is, let's suppose, this much. Okay, so once you get this, and from this, as I said, you will get some program out of it. So because I made a distinction between traditional programming versus machine learning. So till you get a program, this is called as training. Okay, you got a program out of this. So now when you give this program input, okay, so now you got out of this whole process, you got some program. So now through the program you'll give inputs, and now you're expecting some outputs of this program. So this is called as testing. So in the training phase, what you are doing is you gave inputs and outputs. You are telling the algorithm learn the patterns, and it learned the pattern. It came up with this program, okay, some program. It said, okay, these are the patterns which I learned. Now you give me inputs, I'll give you outputs. Now you're giving inputs, you're giving outputs, and this is called training. So this part over here is called as testing, and this part over here is called as training. Okay, and if your data is this much, let's suppose this is your whole data. So what you basically do is you split it into what's called as training set and what's called as test set. If you don't do validation, I'll tell you what validation also is. So training set, usually we do it like this, 70-30 split or 80-20 split. Okay, something like this. We have validation set also, because the whole point is to generalize the algorithm. It should not memorize data set. Okay, that's why we do this. And each of this is a huge topic. Okay, probably we'll take each of the session. Maybe one session will be on just on feature engineering. One session will be on data cleaning. We'll have session on how to let's suppose handle these missing values and stuff like that. And this is the whole course. And then we have this model training also. So model training is how do you train the model now. So in the model training, you'll choose a loss function. So what you would basically do is you'll choose what loss function to use. Okay, how do you quantify is model learning? So you have a loss function, and you also have to see what optimizer should I use. What optimizer, if it is deep learning algorithm, ADAM optimizer is there, SGD optimizer is there, and then training you fit the model. Okay, and then in here also, if your training set is too big, so now you know that I have resource limitation is there. And now I'll have to do batching. We'll use batches of data. You'll do that also. Okay, divide into mini batches, and then for the efficient training. So once your model is trained, you have loss function, you have optimizer, you did this batching, and you kept it on training. Once it is training, then you have to evaluate your model. Okay, so if from this you have to evaluate your model. Evaluate the model. So by evaluation, I mean the performance measure metric P. So you will have this accuracy, F1 score, precision, recall. So all these things will be there. So then you will perform also cross validation. That's why you'll use validation data set for validating the things. Okay, you sometimes what is called as k-fold cross validation. All of these things will be clear. So here what we do is we have different metrics on which we'll measure it. You have different metrics on which you measure it, and you perform validation over here. So once you try to evaluate, so from the validation set, there is something called as hyperparameters. So you will do what is called as hyperparameter tuning. Okay, so you will do hyperparameter tuning. So I'll write parameter tuning just because it's a smaller space. So now you have, let's suppose, learning rate. You have how much batch size should you use, what is the number of layers that you should use. Okay, these are called as like hyperparameters, which you have to set, and you will tune these parameters by yourself. You'll try different values. The algorithms are like they're called a grid search, random search. So these of algorithm we will use to perform this parameter tuning, hyperparameter tuning. So I should write hyperparameter tuning. So you'll tune the parameters so as to get the best result, and this will be done based on this evaluation, based on the validation. So after this, what you do is you do model testing again. Once you have this hyperparameter tuned, and you at the end do model testing. Okay, you will do, now you have test set, and you will do the testing, because once you froze the hyperparameters, once you evaluate the model on the validation set, so after that what you do is you at the end test it by using the test set. So I'll call that model testing. Where should I write it now? So maybe here. So we'll do what's called as model testing. So we'll say model testing. Okay, so it started from here, and I think I should also number them. So this is first thing, this is second step, and this is third, this is fourth step, and this is fifth, sixth, and seventh. In the testing, what I'll do is, as I did validation, I'll do the same thing. I'll say this I have no unseen data. So on the unseen data, how is it performing? Is it overfitting? Overfitting basically means it is memorizing. Is it underfitting? Is it not? Is it perform poorly? So after that, what I'll do is I'll do model deployment. What I should do is I should rather write these 7 steps from here. Okay, so I'll do it from here. So once I am testing the model, now I am having model testing. Okay, in model testing, what I'm doing is again checking the overfitting, underfitting on the test set and checking the different scores. Okay, so once I have that, then I'll do model deployment. So we deploy the model into the real world. That's called as model deployment. Okay, model deployment, what we do is, now let's suppose if your model is being used in a website somewhere, if your model is being used in application somewhere, so you deploy the model. So you export these models and save it with, let's suppose, joblib or maybe .h5 extension. And after that, you have these API. You deploy the model by using web services or maybe an API like Flask, Fast API or something. Then you do what's called inferencing. Inferencing, basically, now you want to infer from the model. So you use this model in the production environment and make predictions on the new data. Now you give it to the users to make the new data. And after that, we monitor it. So at the end, we do monitoring and maintenance. We keep on monitoring and we maintain monitoring and maintenance. So in that, we'll keep on doing the checks of performance. Is it performing good? And we'll do sometimes retraining again. Okay, now we will retrain the model. Okay, now we'll scale it better. Okay, the one example can be, I'll tell each of the steps with an example. Let's suppose one example, I want to define problem. So let's say we want to have a task of fraud transactions. So we have a task at hand, detect fraudulent transactions. So that is the problem that we have. So we defined that our task, our objective is to detect fraudulent transactions. Okay, in the background. What is the objective? Objective is to automatically flag a potential fraud transaction. So if you have a transaction, you have to automatically flag it. Are you following me? So am I speaking too much? Are you following me? Okay. Yes. So I'm saying that the first thing is, so if you now have to define a problem, so the task at hand could be detect the fraudulent transactions. Okay. So now objective is that you should automatically flag a transaction if it is potentially fraudulent, and then it will reduce the objective is it should reduce the financial losses. That is the problem that we have. Okay. So I should write it like this now. So the problem statement that we have is, problem statement is detect fraud, detect fraud transactions. Okay, and objective is that it should flag it automatically. Then we have data collection. So this is our problem set. Then we have data collection. How do we collect data? Now we'll either go to the banks and ask them for the records, okay, and we'll take the customer information, historical reports, and then we'll format it. By format, I mean you can read it in the CSV files, okay, and CSV file will be like this. Okay, so data will be like this. So here we have customer 1, customer 2, customer 3, something like this, account number, CC number, let's suppose. Then we'll have amount, then we'll have transaction ID, okay, then we'll have timestamp. We'll have a lot of records about this. So this is how we'll format. This is formatting of the data, how we'll format the data. And before that, we'll have sources. So sources will be going to the real banks and ask them for the information. Then we'll have to pre-process it, data pre-processing. So in that, if there are missing value, let's suppose if there are timestamps are missing for something, you have to handle the timestamps. Okay. Then you have to create features or this. What you can do is you can create additional features like what is the transaction frequency. So in last 1 hour, how many times the transaction happened, or in last 1 week, how many transactions happened. So because these things you have to do it on yourself. That's called feature engineering. So maybe, or you can say what is the amount deviation. Okay, this was the total amount spent and how much is the deviation. Or you can do a different processing also. So, or maybe you can add some other fields, and then you have to handle categorical data. Okay, once, and then you will split and maybe augment the data according to whatever you want to do it. And after that, you will select a model. Let's suppose if you selected a model into machine learning, like gradient gradient boosting or XGBoost, random forest, or linear regression, logistic, whatever you decide. So once you decide that model, and then you will give this data. Or if it's a deep learning, what you will do is you will decide on the architecture, and you will say, let's suppose I want to use transformers, and I want to use LSTM, I want to use some attention based models. So, and then you will make the whole architecture and you will feed this data onto this. And once you train the model, and you can, let's suppose, say I'll give a loss function which is called as binary entropy loss. So I'll give this binary entropy loss, and I'll use my optimizer which is called as Adam optimizer, let's say, and then I'll fit the model. So once you have that, then you will have a validation set. So you'll compute precision, recall, and F1 score. Usually people have precision, F1, and recall, and F1 score. Basically, F1 score comes up from this precision and recall. And then one more thing is called as AUC, area under curve, is also computed in this case. So then you perform this validation, and then you tune the hub parameters in terms of, let's suppose, deep learning methods. You will tune learning rates. You will turn number of layers, maybe number of neurons per layer, or something. Then you will do model testing. Okay, once you are set with this, so if your split was like this, you have used 70, 15, 15, 70% for training, 15% for validation, and now 15% for testing. So now you'll use this 15% of the data, and you will test your model. So once you are convinced that your model is performing good, then you will deploy the model, okay, by using this API server. You'll deploy the model in production environment by using what I said is by Flask API, or maybe by Flask or Fast API, whatever you use, so that when you deploy it, once any person performs a transaction, it will flag it, it will give it a score, how probable is this transaction to be fraudulent, and it will again accordingly take the next steps. Okay, then we'll keep on monitoring it. We'll keep on monitoring, is the progress going down, and let's check the what's called as model drift. We'll check the model for the drift. Okay, by drift I mean initially it might perform good, but then fraudulent people, they learned, oh, this is how fraudulent behavior is being captured. Now we'll change our strategies. If it change the strategy, now the model is no longer able to predict the fraudulent behavior. So what now we'll do? We'll see a shift in the model. So which we call as model drift. Model has been drifted because it's not performing as it was performing earlier. So that gives us the clue that we need to retrain the model. So because now the fraudulent people, they somehow learned that model is behaving in this way. Okay, and then they'll retrain it. Again, we'll ensure that this model is scalable, and in each step we'll have different actions. Okay, this is the general pipeline. Okay, any questions on the pipeline? So this is the generic pipeline. So we start with problem definition, data collection, preparation, model selection, model training, and then model evaluation, have parameter tuning, and then the three other steps, that is model testing, model deployment, and monitoring and maintenance. Any questions on this?
Sir, in these steps, is there any like timeline? How much time we have to give to particular step?
Usually I won't say there is a timeline. So it depends. Let's suppose some people, if the data is really, sometimes the data is really hard to gather, so this step takes, like, this is an easy step because you define a problem. It might not be that difficult, but some people it might be difficult also. But once you are done with this, so this can be a scary part also. If the data is not publicly available, you have to do the data on your own, and then this preparation doesn't take much time. Okay, doesn't take much time, but by that I mean this is like there are certain set of the things that you do, because it's more of an art also. So if you have done a lot of processing of data, you know what steps to perform. But many of the times you will see that people sometimes assign 60% time to this model, this data preparation. We should prepare data because there is a rule called as garbage in, garbage out. If your data is garbage, your model is garbage. So that's why people spend a lot of time in this preparation of the data. And this model selection is also easy. You have to select the model, you have to design the model, and this training, this is not that difficult. But I hope these things, so initial phases, so this data collection, and then these phases, and then maybe model designing, that's not a big deal. But here you should take you should be very careful and highly careful, because if you give a garbage data to the model, no matter how good the model is, it will still perform like garbage. Yes, I think Anwar has a question.
Yeah. Uh, when we started with the problem, most of the data
Mm-hmm.
models are going to fail. Okay, where exactly, like, whether it is going to fail because of data preparation, or are we failing at the data model selection? Most of the project.
No, in the project, that's what I'm saying. If you have a clear objective, if you have a clear objective in the mind, then the first thing is you should also get domain experts, because sometimes you might have machine learning expertise, but you don't have domain experts. Let's suppose I am working in medical domain, but I have no clue about the medical science. So what I'll do is I'll probably approach domain experts to tell them, so the data I'm collecting, is it right? So should I collect the same data? So they should be the one who should tell me about the data collection and the data preparation also, because it requires a lot of domain expertise. Okay, let's suppose if I am working on detecting cancer, so I myself don't know how to look at this picture. The first thing is I should understand it myself. Once I understand that, otherwise, as I said, it will be a garbage model, because you are giving the garbage data, it will give the garbage output also. So it is better to ask these domain experts to give you the data and check from them. Like, do you think this data is good? Is the quality of data is a good quality data? Then I think once you design the model, it is not a big deal, because if your data is good and then your data collection you did it quite nicely, and then you decide on the model, because it also depends. Every model has certain assumptions, okay, and we'll see that in machine learning. What assumptions does the model work on? Okay, some models work on good on imbalanced data sets where you have less number of majority class, where there is a majority and minority class. Rather, what is the majority class? Where you have, let's suppose, in fraudulent transactions, the data is more transactions are non-fraud, 99% of them. Okay, and some transactions are fraud, but here we want to create a balance. So for that you have to accordingly select the model, and then this is a standard process of model testing, model validation, and then parameter tuning. But I'll say these steps are very important. Till here, I'll say more important, and this is also important, what model to select. And training, you have, and even this training has a lot of challenge, in engineering challenge. Now your models are getting bigger and bigger, so now how to parallelize these models, how to have clusters of models. So this again is a huge topic. Okay, and then evaluation is not that big of a thing, but have parameter tuning also. You have to learn techniques how to tune parameters, and then the whole field of ML ops comes into picture from here. Okay, machine learning operations. So how will you deploy the model, and then how will you continuously monitor, as we have this DevOps and we have this ML ops now also. So DevOps means like web developers, they had to deploy these models. But I'll say most of these problems come in these initial stages. Problems once you are done with this data collection, data preparation and cleaning, and then probably model selection is not a big deal. I hope I answered the question. And but again, to come back at the previous question, there is no hard and fast deadlines. Yes, Anwar.
Yeah, thank you.
Yes, Ijaz is a question. Yes, Ijaz.
Assalamu alaikum, sir. Supposedly, I have collected the data. My data is related to images.
Mm-hmm.
Now I have to annotate. I have to label that data. Is there any data annotation tool? Like we have data annotation tools like label IMG, where we used to annotate the data manually.
Yes.
My question is that is there any data annotation tool where we can annotate the data in bulk?
There are possible tools. But the thing is, human annotation is always better. But because these tools might have also learned annotation from something else. Because and annotation, by annotation I mean it can be captioning also. Let's suppose you have an image and you want to caption the image. You want to add a sentence or two. Sometimes it can be just a mark. You want to mark the image. So the better
Yes,
part is
like my task is I have to create boundary boxes.
bounding boxes. Yes. There are models. There are object direction models where you have something called as faster RCNs with these RPNs in the backbone. Okay, so there you create these bounding boxes in the images. So you have an image, you create the bounding boxes. Okay, and probably we can connect it on different. I'll show you the different models, and you should also check if they are giving the accurate bounding boxes or not. Okay, and there are different algorithms that do work on these, and because it's a famous problem, this object detection is a famous problem.
Okay.
And now, to end this thing, I will tell you why this machine learning has taken off now. Because why this machine, if we had these back propagation algorithm, the most algorithm that we use in deep learning and machine learning, they were already discovered before 1980s or 1970s. So they were already discovered. So the thing we had is now there are two things that boosted up. We have a lot of data now, like tons of data. Now if you see internet, we have a common place where we share a huge amounts of data, so then it becomes easy for us to collect this data. So data is one of the big thing that happened in machine learning. And the second thing is now we have compute power also. We have compute power. So compute power is now we have good resources to crunch these numbers. So once we have these two things, we were perfectly positioned to do the machine learning, because machine learning it is data hungry. At least deep learning is very data hungry. You need to give it a lot of data in order to find the patterns. And one more thing, now there is rapid development of new architectures and algorithms, new algorithms and architectures. I think, but most of these things, these are more important, because we are in an era where we have a lot of data, tons of data available at our disposal. We can scrap the web, and there are repositories where they keep the track of this data, and there are good resources of the data, and you can find a lot of data. If you want to perform a task, you can find the data, and sometimes you might need to create data. And computational power is also there. Now you have companies like Nvidia who are making GPUs, and that's why their valuation, if you see, it increased a lot. Why? Because everybody needs more compute power, and who was going to provide them? Nvidia is going to provide them. Okay, there's a famous quote in business: if you find a gold mine, do not sell gold. Okay, rather push the gold down and sell the shovels. Okay, that's what Nvidia is doing, and the gold mine basically is these large language models and generative AI. Now what they are doing is they are not working per se on that, but what they are doing is they are giving tools to train the models. They have these 800 GPUs now. They have a lot of different types of GPUs, and they are almost breaking every boundary. And these things are very competition expensive things. So if you see, this compute power has increased lately, and this data, this now in the internet era, in the big data era, so we have a tons of data, and these two are the main factors because of which machine learning took off. And one more thing I'll add here is open sourceness. So many of these things are open source, Okay, people did not try to just do it behind the wheels and did not show it to the world. Many of the people, because it was being bashed everywhere, AI was being bashed everywhere. No, this is not working. People are over promising. What people did, whatever they were doing in AI, they were putting it in public, and public has a lot of power. Like, and people started contributing a lot. So open source is one of the main important aspects because of which it became famous. And that's why even if you see right now, ChatGPT released a model and they did not make it open source. They just we have a web interface to access it. But after that, we have a series of llama models, and then a French company, I think Mistral, and they release these models. And now, the more open source it becomes, the more people are there to experiment with it. And that's why when you have more people, you have more intelligence. So more intelligence creates much good products. Okay, that's why this data, this compute power, coming up with new algorithms and open sourceness. This is why this thing is sort of taking the hype, and it is so rightly taking it right now. Okay, and because it is, the history has never seen a thing like this happening, where we are this close. It is writing the perfect things, and it is speaking. We can create videos, we can create images. Do not think it as just a different tool. It is entirely going to change different realms. Okay, because we are trying to automate different things. The lives are going to get better, maybe in different areas, and maybe sometimes some people might get their lives might get worse also because of the loss in jobs and stuff like that. Okay, but these are the important four things which I would say, because of these four things, AI took off, and still we are in the bubble, and we have not reached the peak. People are saying we haven't reached the peak, and yet there are a lot of things to come. If you see recent release of I think O1 or something they call it, from ChatGPT, it was it is good at reasoning now. It's way good at coding and stuff like that. Okay, and they show these emergent behaviors. So we will have separate discussion on the generative AI. With this, I'll close today's session. I hope that you people enjoyed the session. I'll stop the recording. If you have any questions, please do ask.